Welcome back. We are now going to study one of the simplest of the formal language machines that this course will introduce. This is the deterministic finite state automaton. Deterministic finite state automata are foundational to models of computation. They are basically also called state machines. They take symbols from an input, and after seeing a sequence of symbols, which is called a string, the DFA may accept or reject that string. So you can think of deterministic finite state automatons as string classifiers. It has a set of strings that it likes to accept, and that will then be called the language of the DFA. And then there'll be a set of strings that it rejects. That'll be the rejected set of strings that is in the complement of the language of the DFA. And if you take the set of strings accepted and the strings not accepted and take a union, you will get the universe of strings that we are working with. Okay, so let us try to load this module, which is basically a blank Jupyter notebook being run in Colab, and define a simple deterministic finite state automaton that recognizes the language of all strings whose second last symbol is a 1. Not the last one, but the second last, the penultimate. So it accepts any string that ends in a 1, 0 or a 1, 1, you can say. And the beginning is not important. So once we load this module, let us see how we can proceed. So you basically insert code cells and then type more code cells as you feel the need. So DFA for second last is 1. Okay. So in the markdown notation of Joe, we can introduce a machine directly. So you can call it something, second last 1. Let's say maybe shorten it, second last is a 1 equal to, and then you say markdown to machine, and then you say the type of machine that is being encoded is a DFA, and put Python triple quotes so that we can fill the intervening space with whatever you want, either comments or transition lines. Okay, so the machine starts in an initial state, and clearly it cannot accept an epsilon, which means it cannot accept empty strings. So the initial state is not a final state. The initial state is just an initial state. And what do we do upon seeing a 0? That is something you have to fill up. And what do we do upon seeing a 1? Now, the second case is more interesting because when you see a 1, it could be that the machine has seen the penultimate 1, in which case it just needs to see one more. So does it matter if it sees a 0 in the initial state? Does it need to record the 0? Does it matter in the language I described? Well, it is the initial state, and the 0 is not going to assume any significance as far as the second last goes. So why don't we think a little bit and conclude, perhaps rightly so, that the 0 is not important right away. So forget the 0. And some of these steps will have to be thought again, but you are trying to imagine the state diagram, and you may even draw it on a piece of paper, but we could even draw as we proceed, which I will show in a second. So suppose after a 1, we need to remember the 1 in the state, because that 1 could play a role. What I suggest is to name the state with a letter that also attaches the string so far or some condensed information pertaining to the string so far. So let us say we are keeping a window of strings that you need to remember attached to the state. So this would be the oldest, and then the next older, youngest. That is the kind of history I'm going to keep. So it also looks like what you fed first, followed by what you fed again, etc. So suppose I call this the state one because that is the only thing that we need to remember. And that is also the oldest and the youngest. Okay, so at this point, we could be drawing the machine also because that way we can interactively fill the machine. Dot object DFA, and then second last one, and then also give fuse edges equal to true. This actually helps draw the machine with zeros and ones fused up. Okay, so far so good. We have described an initial symbol that has gone into the machine. What happens in state one when you receive something else? I'm going to align these for better readability. Generally, I like to align these. So at this point, S1. So if S1 sees a 0 or a 1, then the one that it has seen before has acted as a penultimate one. But do you need to remember what you're seeing next also? A moment's reflection convinces you that what you need to do is remember what you see next, because suppose I were to see a 1 again, well, that 1 can not only be the last symbol, but also serve as the penultimate symbol for string symbols yet to come. So suppose I see a 1, and the machine has now seen a 1 followed by 1. So there is a penultimate 1, or second last is 1. So try to remember in the final state that you're going to attain the fact that you have seen a 1. Okay, so let us call this state the F11 state, signifying that you have seen 1 followed by 1 as the last 2 bits, and the state is final. Okay, so at this point, if I just try to shift enter, it'll fill that detail. Okay, so what would be the transition for 1 0 0? Again, now it tends to remember the fact that the last symbol seen is a 0, but the penultimate is a 1. So it is still a final state, but it remembers it in a different final state. So F10 and F11. Okay, so far so good. All right, so now S1 has been fully decoded and I has been fully decoded. If you want to put these together to visually suggest that these have been fully decoded, you may do so. Now, if I take F11 and give it a 1, then where should it go? Moment's reflection tells you that you are going to still see the last 2 bits as F RS11, and that encourages you to go back to F11 itself. So that is the right thing to do. Now, if I try to come to F11 and feed it 0, so now the history is 1 0, and there's a state for that, F10. Okay, so at this point, you can go to the state F10. Now, what does F10 have to do? Now, F10, if I see any symbol, the 0 that was seen the most recent will not be this penultimate 1 anymore. So we cannot keep that in the final state anymore. And the last 2 bits now will suggest a history that you're going to keep, which has to be in a certain state, which is non-final. And a non-final state can be started with a letter such as S. And should I keep F10 0? Should I keep 3 bits or should I keep 2 bits? Okay, so there is a thought process that you have to go through. So suppose I religiously follow the idea of keeping just the last 2 bits seen so far, in which case I'll transition to S00, in which case F10 with a 1 will go to S01. All right, so again, I'm keeping 2 last bits. All right, so these are non-final states. And now we can finish up S00, S00 upon 0. It's clear that, again, a 2-bit history can be maintained by keeping S00. Again, that doesn't change the penultimate status of any symbol. Now, if I do S00 followed by a 1, then what do I do? I'm keeping a history of S01, 2 bits again. Now, if I do S01 and follow it with a 0, where should it go? So now the last 2 bits are 1 and a 0. So it is a final state. And we have the state name for it, which is F10. And S01 followed by a 1, where should it go? Again, we have a state that corresponds to it, which is F11. So we could draw this much. All right, so are we done? Or can we optimize the machine a bit more? Or are there missing undecoded states? So we did F11, F10. Did we ever have to go into S01? Yes, we did. And S01 suggests that the last 2 bits need not, the last 2 bits are such that the penultimate symbol is not a 1. So S00 is fully done, S01 is done, F10 is fully decoded, F11 is fully decoded. So this machine appears to be fully decoded. And there is a little worry that we may not have put in enough transitions. So let us make sure that we have covered everything. So there is really nothing missing, except why should we keep state S with a 1 following it as different from a state I, which filters away the 0? So could we have named, in other words, what I'm saying is, could we have named this more uniformly to be an S0 state where it actually remembers the 0, in which case all our conventions jive up, meaning I is a state where nothing has been seen. S0 and S1 are states in which 1 symbol has been seen and they have been fully decoded. So if you want to keep the machine symmetric and keep track of all the symbols seen so far up to 2 last symbols, basically, then S00 can be a state that is already available for S0, and S0 followed by a 1. Where should it go? Again, it is going to only go up to S01 because it has not seen the penultimate 1. So suppose we change the machine to be like this. So then it actually is a very symmetric system where you have states S0 and S1 after seeing 1 symbol. And after seeing 2 symbols, you are in F10 or S00. And then the transition diagram folds into itself. So this machine allegedly does what we sought out to do, which is recognize all symbols, all strings where the second to last symbol is a 1. So at this point, we could actually animate the machine, and we could also subject the machine to some of the executions that we had tried. So let us try to get an animation panel ready for this machine from somewhere else. There are acceptance loops that we have written before. And let us take one of the animations because it seems to be a preferred way of animating the machine that we have studied so far. The animation panel will be, here it is. It is not in this machine description. So let us take it from the overview. The overview has ready animation panels for most, as a template for DFA and for other machines. So we could take this one and Joe editor and display, yes. And that is the full animation panel, including all the machines. Suppose you want to specifically animate DFA, that is available here. Okay, so I'm going to take the animation from here and put it in here. And we'll change the names of the machine involved, which is going to be, so here it is second, the last one. And I like a few edges equal to false sometimes because then you can see the separate transitions. So let's give this a go. So at this point, it is ready to animate the machine. So let's try 0, 1, 0, 1, 0 and animate at this point. Increase the speed and see what it does. So it occasionally attains the acceptance whenever there is a penultimate one symbol, and at the end of the day, it has finished accepting. So now you can also see what kind of a machine we developed. We can just print it out again to review, second last one. And it is a Python dictionary or Python hash table, which has all the states named in the queue list or set of states. Sigma is 0, 1. This was recognized by reading the input here. And the delta itself has key values listed here. So the key is upon state as 0, upon seeing 0, goes to S0, 0, like that. And the initial state is where we start with, and F1, 0 and F11 are the final states. Okay, so this is a very gentle introduction to DFA, which are finite state recognizers that recognize set of strings and classifies them as accepted or not. Okay, so suppose that one's ambition now climbs to model third last is one. Okay, so DFA. So now the state that you have to maintain has to be a bit more elaborate, because you are going to remember up to 3 bits of the initial of the string seen so far. So I'm going to copy region and copy selection and paste it and modify it. That would be a good way to arrive at it. So I'll call this the third last is one, or TRD, last one. Okay. So now let us say that we are keeping the state structure similar looking. And what happens when you come to S11? That won't go to the final state because we haven't seen a third last. So we'll have to extend this to S11 and S10. Okay. So far I'm maintaining 3 up to the last 3 bits seen so far. And now let us not get into the remaining states that can be distracting. So far, so good. S0 and S1 have been decoded, thus creating us for us S00, S01, S11, S10. Okay, so suppose I now take on S00, and if I give it a 0, then the last 3 bits seen so far is S00, and it's not a final. S00 upon a 1, where does it go? It actually now has to record the 1, because that 1 could end up being the second last. Okay, so S001. How about S01? S01 ends up again not recognizing. It is not attaining a third last being a 1. So it remembers S010 and S01 upon a 1. Again, it has not filled the third last position, so it is S011. And now, so S01 is dealt with, S10. So suppose I come to S10, and if I see a 0, where should it go? So now we see that the third last symbol is indeed going to be a 1, so it has to be an F, and it remembers F and then 100. S10 followed by a 1. Again, now it goes into F101. Okay, so now S11 is the last remaining. So upon a 0, it goes to F110, and S11 upon a 1 goes to F111. Okay, this is a straightforward set of thoughts that we engaged in, and we just typed in the state name that remembers the relevant bits seen so far, and the relevant bits seen so far encodes enough information to recognize the correct set of strings. Are we now done? Can we now finish up the machine? So S has been decoded up to 2 symbols, and there are 3 bit sequences that need to be carried out. S00 upon a 0 goes to S000 because you can forget that. S000 upon a 1 goes to S001, which is also a state that's available. How about S001? Okay. S001 upon a 0 goes to S010. S001 upon a 1 goes to S011. All right. So far, so good. Okay. So S00, S01, okay, S010. Is there any other state that we have? We have not named any other S states because if the third last bit is a 1, that is an F state. So that is all we have created so far. And suppose I have to build a further S01. S010 has to be dealt with. It has not been subject to any decodings. If I do a 0, where should it go? Again, the bits shift to the left, so to speak. So it becomes F100. S010 upon a 1 goes to F101. All right, because the bits shift again to the left. So now what happens to other states, S010? So which states remain? S010 has been decoded. S011 has not been decoded. S011 has not been decoded. Upon a 0, it again goes to F because it shifts left. F110. S011 upon a 1 goes to F111. Okay. So now we have exhausted all the S states, and we just need to now finish up the F states. So then none of the F states have been decoded. So let us do that. F000 is not there. F001 is not there because all the F states have a 1 sitting in the first position. So F00 has to be decoded. F101 has to be decoded. F110 has to be decoded. And F111 has to be decoded. These are the 4 F states we introduced. And let us go through them. And the design is going to be pretty straightforward. F100 upon a 0 would have seen 3 zeros. So it is going to go back to S state. F100 upon a 1 again pushes the states seen to the left. It becomes S001. F101 seeing a 0 goes to the left, and it becomes an S010. F101 on a 1 goes to S, because again that 0 shifts to the left, 011. And now F110 upon a 0 goes to, now there is another one that comes into the third last position. So it is F100. F110 on a 1 goes to F101. All right. So how about F111? That's easy again. F on a 0, it goes to an F state, 110. And F111 upon a 1 stays back in F11. And we can draw the third last one in one shot. Okay, so we have actually exponentiated the number of states, it looks like. So we had how many states in the previous? 1, 2, 3, 4, 5, 6, 7 states. And it has become 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that right? Yeah. So how many states did we have? 1, 2, 3, 4, 5, 6, 7 states. And how about 1, 2, 3, 4? That's not a good way. So let us count the number of states using the length function. Okay, there is something else that is not decoded, F11. What happened to F11? That is an orphan state. So that was not properly typed in. That's the reason why I got a certain surprising number of states. Okay, so now the machine seems to decode and be fully connected and things like that. Every state seems to have 2 transitions going out. You can eyeball and check that. And there is also is consistent that you can do. We can apply that right now and see. So is consistent is consistent DFA of third last one, and see if it's a consistent DFA. So it's consistent, it has decoded. So at this point, third last one of Q and the length function will tell us how many states? 15 states. So now it seems to follow 2 raised to n minus 1 exactly, which is what we are observing. And we can mathematically prove that you cannot escape exponentiality for this language. If I now go to the fourth last is one DFA, it would create 2 raised to 5 minus 1 or 31 states. There could be something redundant about this DFA. We just let our thoughts flow and created it. So let us do minimum min of third last one as a check, and equal to min DFA of third last one. This is always a good check, and then we can see the length of that. And if it has reduced it, we know that our design was inefficient and we could have saved some states. So we can do min and then see. It is 8. So we could have done it in 8 states. That's what we are seeing. And how so? So let us draw this out. So dot object DFA of min third last one, and use edges equal to true. It's not needed, but all right. So now what we see is we can actually save introducing a state by spinning here upon a 0, which was our original decision. Whereas here we decided to fork into 2 different states. So suppose we do that, then the multiplicity of these 2 states is eliminated. So I and S0 become equalanced. And because they are equalanced, all the further transitions that lead out of I, lead out of S0, get the benefit of the optimization. That seems to be the story. So we could have done it in 8 states. And the same goes for the previous DFA. So suppose we had done it in lesser number of states, even from the beginning by collapsing out. Or could we have attained a smaller design? So let us pursue that and see where we end up. That'll be the subject of following recording. Okay. So at this point, you know that the basic path of defining state machines is by thinking through the state encodings and, of course, checking your work and seeing whether you got a minimal form at any point. We'll come to whether we can achieve the minimal form directly, but the proof is that the minimized form cannot be done in fewer than 8 states for the third last. So that actually is something that we can take up in another lecture. Bye.